Welcome everyone to this week's Science News. Today we'll talk about the possibly first evidence for life on an exoplanet, with some caveats, chaos at the center of the Milky Way, earthquake lights, a really old rock, noise cancellation for qubits, good news about air pollution, Wi-Fi that can see through walls, origami robots, the 2024 Breakthrough Prizes, and of course, the telephone will ring. A group of scientists from the UK might have found the first signs of life on an exoplanet with the James Webb Space Telescope. The planet's name is K2-18b. It's about 120 light-years away and it orbits a cold dwarf star in the constellation Leo. It was originally discovered by the Kepler Space Telescope and is estimated to have about 9 times the mass of our planet. In the new paper now, the scientists report using the spectrographs on board the Webb telescope to inspect the chemical composition of the planet's atmosphere. Data from Hubble had already revealed that the atmosphere is mostly hydrogen and possibly contains water vapor. The new analysis now found carbon dioxide and traces of methane and dimethyl sulfide, which could mean that there's life on this planet. Here on Earth, these chemicals come from living organisms. Indeed, on Earth, dimethyl sulfide is only produced by some types of algae. It has no other natural source. The researchers also point out that there is little ammonia in the atmosphere of the exoplanet, which could mean that it's covered by liquid water, because that could absorb the ammonia. Before you get too excited, K2-18b receives much more high-energy radiation from its sun than we get from ours, which is not great for life. But to sum it up...
So you're telling me there's a chance?
A team of astronomers at Leiden University in the Netherlands say the motion of stars in the center of the Milky Way is far more chaotic than previously thought. Back in 2018, the astronomers developed a computer algorithm that could calculate the future motion of stars from measurements of their positions in the past. They've now applied their algorithm to predict the orbits of 27 stars circling the black hole in the center of the Milky Way from the input data we have. They found that these stars are so close to each other that their orbits become chaotic very quickly, in just about 462 years. It's like all this general relativity is too confusing for the stars and they kinda space out. This motion will also affect the black hole itself. The astronomers estimate that this makes the black hole's vicinity 30,000 times more chaotic than our own solar system. Yes, the orbits of planets in our own solar system aren't stable either. They'll eventually destabilize too. The most likely thing to happen is that the orbit of planet Mercury destabilizes first, because Mercury is fairly small and has the misfortune of an orbital period that's quite but not exactly synchronized with that of Jupiter. If Mercury's orbit destabilizes, it'll either be kicked out of the solar system or fall into the sun. Either way, it'll be quite a spectacle. And it'll happen in just about 5 million years or so mark your calendar. Albert is super excited too. On September 8th, an earthquake of magnitude 6.8 hit Morocco at around 11 p.m. local time, destroying entire villages and killing several thousand people. Several reports from Morocco have now emerged from people saying they saw strange lights in the sky just before the earthquake hit, and who shared their footage on X, formerly known as Twitter. These are earthquake lights. Anecdotes about them can be found already in ancient Egyptian, Chinese and Japanese documents. These lights typically last a fraction of a second to several seconds. People have reported seeing them before, during or shortly after large earthquakes up to several kilometers away from the epicenter. It's not the first time they've been caught on camera either. A video from an earthquake in Peru in 2007, for example, shows the same phenomenon. The video in Peru was coincidentally captured by geologists who were eventually able to confirm that the lights coincided with peak ground acceleration. So these earthquake lights are definitely real, but exactly what they are, no one knows. Some earthquake lights are probably caused by electrical transformers popping, but this doesn't explain all of them. Some seismologists think piezoelectricity might be to blame, that is, an electrical response that some solid materials have to stress. But some of the observed earthquake lights last too long for that explanation to work, so that's probably not the full story either. Personally, I think it's that aliens interpret earthquakes as ground giggles, and they can't help but take a picture. To have good lightning, they need to use a flashlight, of course, so there you go. Physicists from Caltech and MIT have borrowed a principle used in noise-cancelling headphones to extend the coherence time of certain types of qubits. Qubits or quantum bits are what quantum computers compute with. Unfortunately, their quantum properties usually fade away very quickly. How long the quantum effects last is measured by the decoherence time. For the quantum bits that these researchers were interested in, that's nuclear spin states, the decoherence time is just about 150 microseconds. You might have heard of these as nitrogen vacancy qubits because they're created as defects in certain solids. The problem with these qubits is that since they sit in an atomic lattice, their coherence time decreases due to interactions with the surrounding atoms. In the new paper now, the researchers point out that the nuclear spin state tends to be correlated with an electron spin state, albeit weakly. If they drift off their original state due to noise, they usually do so both the same way. The researchers then suggest applying a laser pulse that flips the electron spin, which in return couples back to the nuclear spin and counteracts the decoherence. They showed experimentally that this actually works. In their experiment, they could extend the qubit's coherence times by a factor 20 to as much as 3 milliseconds. Now, you might argue that 3 milliseconds still aren't much, but I can tell you from my own experience that when it comes to quantum computing, staying coherent for 3 milliseconds is no small feat. A meteorite found in the Sahara Desert is reshaping our understanding of the solar system's early days. The meteorite was found in Algeria in May 2020, so it's a fairly recent find. It had landed in part of the Sahara Desert called Erg-Chech, so it was named Erg-Chech 002. Its mineral composition makes it what's called an ungrouped achondrite meteorite. What's that? A lot of meteorites contain small roundish inserts of a few millimeters in size that are made of some kind of mineral or glass. The inserts are called chondrules, and the meteorites with these inserts are called chondrites. Those which don't have them are called achondrites. This Erg-Chech meteorite is of this type. That it's ungrouped means it doesn't fit into any of the known classes of achondrites, which makes it particularly interesting. One can determine the age of space rocks like this from radioactive decay chains. Since these rocks are so old, you don't date them on Tinder, you date them by using something that decays very slowly. Frequently used are two different decay chains of uranium that eventually lead to stable lead isotopes. That's uranium-238 with a half-life of more than 4 billion years and uranium-235 with a half-life of about 700 million years. This method works well because scientists have a pretty good idea of what the original ratio of the uranium isotopes was. Another interesting compound in those space rocks is aluminium. This comes in two isotopes, aluminium-27, which is stable, and aluminium-26, which decays to magnesium. This decay is not all that great for dating something very old because it has a half-life of only 700,000 years. This is also why, however, its decay is believed to have generated a lot of heat in the early days of our solar system. This is why scientists want to know how much of the stuff there was around back then, and there has been some controversy about this. In the new paper now, researchers used the uranium-lead dating to infer the age of the rock, which came out to be a whopping 4.56 billion years. They also measured the aluminium isotopes, and now since they knew the age, they could calculate back to what the ratio of the aluminium isotopes must have been. They found that the ratio must have been much different in this rock than in other samples, and that therefore the distribution of the aluminium isotopes in the early solar system must have been very different in different places. This is interesting because it tells us something about the geological processes in the formation of solar systems, and questions such as what kind of minerals are likely to be found in which kinds of asteroids or planets. The dating methods of physicists are really underappreciated. Speaking of radioactivity in space science, the American Physical Society has published an opinion piece demanding that astronomers rename the Magellanic Clouds, because Magellan was a bad person. Sooner or later, someone will figure out that the month of July is named after Julius Caesar, who was not exactly a nice guy either. Researchers in the United States have taken a look at the world's efforts to reduce air pollution, and their findings are a rare case of good news. The amount of fine particulate matter in the air is known to be strongly correlated with health problems, mostly affecting the lungs and cardiovascular system. A major source of fine particulate matter is the burning of fossil fuels, which leads to emission of ash and soot. The smallest of those particles can linger in the air for a long time until rain washes them out. It's not just unhealthy, it also contributes to global warming, because the stuff is mostly black and absorbs sunlight and retains heat. For the new study, they used data both from satellites and ground monitoring stations for the years 1998 through 2019. They found that the concentration of fine particulate matter rose from about 28 micrograms per cubic meter in 1998 to almost 39 in 2011, but then dropped off after that. By 2019, exposure to fine particulate matter in the air was down to about 35 micrograms per cubic meter globally on average. That's still more air pollution than we had in 1998, but at least we're on the right track. The biggest change comes from China, which introduced regulations in 2010 because they didn't like their title as global top polluter. The Chinese government enforced the installation of exhaust filters, closed coal mines, and began to electrify much of its public transportation system. Within 8 years, fine particulate matter exposure in China dropped by 15 micrograms per cubic meter, which made a big contribution to bringing down the global average. But it's not just China. Regulations on emissions have led to air quality improvements in many countries, including the United States and Canada, though emissions increased in India. But overall, the air quality improvements have helped reduce the number of health complications and premature mortalities. In case this made you feel optimistic, wildfires are a big contributor to global air pollution. We've seen a lot of those recently, and no, I'm afraid chopping down all trees is not a good solution. It seems we're getting a little closer to the X-ray vision you read about in comic books. Researchers in the United States have created a way to see through walls using Wi-Fi signals. Not only can the Wi-Fi figure out what's on the other side of the wall, but it can also read letters through the wall. Their system works with 3 off-the-shelf Wi-Fi transmitters, a Wi-Fi receiver mounted on a wheeled robot, and an inanimate object. The transmitters and receiver are placed on one side of the wall, while the object's on the other side. The transmitters send radio waves at about 5 gigahertz through the area. That's a typical frequency for a home Wi-Fi. The robot moves around to see where and how those waves bounce back. The amount of power the waves have when they reach the receiver builds an image, allowing the operator to see what's behind the wall. The researchers tested their system with a number of inanimate objects, including letter cutouts that spelled the word believe. Sure enough, the receiver was able to capture how the transmitter's wireless signals interacted with the letters, enabling the team to view an image of the letter behind the wall. But don't worry, no one will be reading over your shoulder from the other room anytime soon, unless you cut out letters from cardboard and hold them up when you read. It'll soon be unnecessary to spy on your reading anyway, because we'll all have brain implants connected to the Google Cloud. Remember when we talked about origami printing methods last month? Well, it seems the art of folding paper has inspired yet another invention. Using the principles behind origami, scientists in the US have developed tiny folding robots that they call microflyers. A single microflyer weighs about 400 milligrams and is just a few square centimeters when unfolded. Attached to each microflyer is a Bluetooth microcontroller powered by solar cells. The idea is that the microflyers are dropped from an elevated area in their flat state. The Bluetooth controller can then be used to change their shape, which affects how they fall. The researchers say simple and cheap microflyers like these could help disperse sensors quickly across large areas where needed. For example, to measure humidity or temperature, or maybe to find signs of life after an earthquake. Hello? Hi, Rishi. They invented what? A ball that mimics your breath? To make people feel more relaxed and focused. Well, that's breathtaking. Sure, thanks for calling in. Bye. The Breakthrough Prizes for 2024 were announced a few days ago. They'll be awarded in April next year in a gala in Los Angeles that has been marketed as the Oscars of Science. The Breakthrough Prizes in the life sciences were awarded for genetically engineering T cells that are part of the body's immune system and that can be coaxed into fighting cancer. The development of a new drug against cystic fibrosis, that's a genetic disease which causes the lungs to clog up, and for identifying genetic risk factors of Parkinson's. The Breakthrough Prize in Mathematics was awarded for research in differential geometry. That's the description of curved spaces and surfaces and what happens on them. It's used in a lot of applications in physics. And the Breakthrough Prize in Fundamental Physics was awarded for contributions in quantum field theory and statistics, which sounds pretty boring, but is the basics of a lot of research in areas from condensed matter physics to astrophysics. The Breakthrough Prizes are $3 million each and are an initiative founded by a group of rich people, including Sergey Brin, Mark Zuckerberg, and Yuri Milner. The prizes were first awarded in 2012, and after attracting some initial criticism for honoring string theorists, the committees have in recent years selected very worthy people indeed. The two physicists are easy to identify among this year's winners as the two old men. They are hugely deserving, of course, but it goes to show how little has happened in fundamental physics in the past 40 years or so. Thanks for listening. We'll be back next week.